All right, so now we're going to talk about PDEs with without time dependence, so in particular elliptic PDEs. Okay, so the prototypical example we're going to look at is what is known as Laplace's equation. Okay, so it looks like uxx plus uyy equals 0. And so this is defined on a domain omega, which is contained in R2. And then what happens is that usually you introduce boundary conditions on the boundary of omega. So you have a region omega, right, which is contained in R2, and then you specify the values that's like on the boundary of omega. Okay, so in particular, it's like we're going to look at the Dirichlet problem. Okay, and this arises when you study things like heat, electromagnetism, and many other sort of physical problems. So it arises heat, sort of electromagnetism, and many other physics problems. Okay, so what you want to do basically is the following, right? So again, you have the following PDE. It's like with boundary conditions, uxx plus uyy is equal to 0 in this domain omega, and then uxy is equal to some function, let's call it gxy, on the boundary. And then we want that u is continuous on the closure of this. Okay. All right. So so under some mild restrictions, on the domain and of G, which is the boundary data, is continuous, right? Then you can show that the Dirichlet problem is well posed. And in particular, that means that there's a unique solution. Okay, so for simplicity, we're going to look at a case where this omega, this domain, is a rectangular region. It's like in R2. And in that situation, you can solve this analytically using series expansions, say using Fourier. Okay, but we're not going to sort of pursue it's like the analytical route. What we want to do instead is to introduce a discretization of this Dirichlet problem using sort of a finite difference perspective. Okay? All right. So let's go ahead and see what happens. So as before, it's like now you're going to have data, it's like on some sort of lattice. It's supposed to be uniform, I'm just not very good at drawing it. But this is in X and this is in Y. So one very natural approach to discretize this is through what is known as finite difference. And we've seen something like this when studying sort of the heat equation, right? Where again you discretize, it's like by sampling, it's like the function values, it's like at sort of discrete points in space as well as in time. So now it's like there's no time dependence in the problem, but there's sort of two spatial dimensions. So you have a lattice, if you will, it's like of points in two spatial dimensions. Okay, so so you want to approximate this equation, okay? So I'm just going to set it up. So let's call it xi yj, right, as I times h, j times h. So here I'm going to assume, so there's going to be a spacing h in both the x and y directions, okay? So I'm going to assume sort of a uniform mesh in both directions, okay? And then, so I and j are between 0 and n plus 1, and then h is just going to be 1 over n plus 1. So here I'm going to look at omega just being the sort of the unit square, right? 0, 1 cross 0, 1 contained in R2. Okay, and then I'm going to sort of mesh it up in the following way. Okay. So, so if you recall, it's like when we were talking about the heat equation, one of the things we did was to use a second, central difference approximation of the second derivative term. And so we're going to do that in both x and y, right? So, so uxx plus uyy equals to 0 is approximated using finite differences. As follows. Okay, so uxx looks like 1 over h squared multiplied into vi minus 1 comma j minus 2 vij plus vi plus 1 comma j. So this sort of the index which is changing is the I term, right? So that corresponds to the x positions. So this is a second derivative. It's like an approximation of the second derivative in x, right, at the point xi yj, if you will. Okay, and then you do the same thing. It's like for the derivative now, it's like in y, right, the second derivative in y, 1 over h squared vi j minus 1 minus 2 vij plus vij plus 1, all right? And then that thing is equal to 0. Okay, so one way to sort of think about this is that if this is the point xi yj, then that stencil, if you will, involves these points sort of, you know, surrounding that point here. Okay, all right, so you can collect all of that. Then what you get is you get 4 vij minus vi minus 1 j minus vi plus 1 j minus vi j minus 1 minus vi j plus 1 is equal to 0. Okay. Then you assume that on the boundary, it's like the information is prescribed. So the boundary values are prescribed. Right, and the way you do this obviously is that v0 j, right, is equal to g at 0 comma j times h, right? And then v1j is equal to g at 1 j times h, and vi0 is equal to g at ih comma 0, and then vi1 is equal to, sorry, maybe it's 1 is not the right way of thinking about it, vn plus 1. Right, g ih time ih comma 1. Okay, so this is the boundary data which you're prescribing. So again, you have a lattice. It's like of it's like going from 0. It's like to n plus 1 in both x and y, right? And you know all the values. It's like on the 0th column and the nth plus first column, and the 0th row and the nth plus first row as well. Okay, and so anything which is left is in the interior. Okay. All right. So, all right. And then we want this condition to hold for I and j. It's like between, well, between 1 and n, basically. Right? And then it's like, yeah. Okay, so so let's look at how this looks like. Okay. So the way you can do this is that you're going to choose a particular ordering, if you will. It's like of the lattice. So you have to enumerate. It's like all the entries. It's like in this lattice of points. It's like so that it you can form a vector. Okay, so we can consider the natural ordering of the vertices of the entries, right? The following natural ordering. Okay, so V is going to be V11, V21, V31. All right, so I'm incrementing X, so I'm going across row by row. Right. Okay, and then V12, V22, V32. Let me just erase that as well. Then V13, V23, and V33. Right, so these are the 9 unknowns. Okay, when you have this lattice, I mean, of course, it's like it can be generalized further. It's like to a finer mesh, but for now, let's just do it this way. So then you have equations. It's like for each of these, right? So 4 times V11 minus V21 minus V12 is equal to, all right, so you want the thing on the left-hand side to be written as a matrix vector product, and the thing on the right-hand side, as we've seen before, will involve the boundary data. So this will be V10 plus V01. So the reason why this is on the right-hand side as opposed to the left-hand side is that V10 and V01, right, do not involve points which are in this vector of unknowns. They involve points which are on the boundary when you know the function values. Okay, so this stuff you know on the right hand side, this is the stuff which you're trying to solve for. Okay, so this is why we've ordered it this way, and then for v21 minus v11 minus v31 minus v22, right, is equal to v20. Okay, so maybe I should draw this out for you, right? So this is v11, this is v21, this is v31, v12, v22, v32, then v13, v23, and v33, right? And then in addition to that, you have the stuff on the boundary. So this is v10, and then this is v01. Okay, so if you recall, it's like the coefficients involved 4 here and then minus 1s on the adjacent things, right? So I'm just looking at essentially the first equation now. And the stuff in red is the stuff which you have prescribed to the boundary data. So there are minus signs when they're put on the left, but I moved them to the right so that the plus sign's there. All right, so this is where that first equation comes from. And the same thing happens here, right, is that, you know, it's like if you just sort of wrote down what's happening, it's like when you're centered about the point v12, there'll be an entry here, right, corresponding to v02. But v02 again, sorry, v21 is here, right? So v21 is here. This is v20, okay? So v21 is this entry. There are these sort of 4 points around it, right? And there's a v20 entry, but it's on the boundary again, so I put it on the right-hand side, which is why this is on the right-hand side. Okay, so hopefully that gives you an idea of what is going on, right? The things which are part of this vector of unknowns, I keep on the left. The things which are prescribed by the boundary data, I push to the right. Okay. All right, so I can keep going. So this is 4v31 minus v21 minus v32 is equal to v30 plus v41. Okay, and then 4v12. So I'm just going to keep writing this. Okay, and so on. Okay. All right. So in any case, what happens is that you end up getting a, it's like a system of equations which can be written as a linear system in the form. So you can write this as a linear system. Ax is equal to b. Or actually, AV is equal to b because the unknown vector is v. Okay, where A obviously is a 9 by 9 matrix. And then of the 81 elements, it's like in this 9 by 9 matrix, only 33 of them are non-zero. Okay. All right. So what I'm going to do is I'm going to write this matrix in a sort of very clear blocked form. Okay. So A looks like the following. Okay. And it's going to be, so if you recall, it's like this vector, right, reflects some sort of lattice of 3 by 3 points, 9 points. Okay. And as you might expect, this matrix A is going to have some sort of blocked form, which I'm going to write like this. Okay, so there's a 4, 4, 4, minus 1, minus 1, minus 1, minus 1 here. There's a minus 1, minus 1, minus 1, and these are zeros. This is the 0 3 by 3 block. There's a 0 3 by 3 block here as well. All right, that's minus 1, minus 1, minus 1, minus 1, minus 1, minus 1. Okay, minus 1, minus 1, minus 1. And then this is repeated, right? So there's a 4, 4, 4, minus 1, minus 1, minus 1, minus 1, 0, 0, 4, 4, 4, minus 1, minus 1, minus 1, minus 1, 0, 0. All right, so if you look at this block, there are basically three main types of blocks, right? There's the 0 block here, there's minus the identity here, 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 and here. And then there's this, sort of block with 4s along the diagonal, and then minus 1s just up by 1 and down by 1, and the 0s elsewhere. And this shows up along the diagonal, right, in this way. Okay, so this is what A looks like. So I can write this in some sort of notation. So I can write A in this blocked form as T, 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 minus the identity, minus identity, minus identity, minus identity, 0, and 0, right, where T obviously is just 4, 4, 4, minus 1, minus 1, minus 1, minus 1, and 0, 0 here. Okay, all right. Yeah, so that's what it looks like, and it's like you can you can see it's like that. Again, it's like solving. It's like this Dirichlet problem using finite differences just involves essentially inverting this linear system for this A matrix, and then a right-hand side which depends on the boundary data. So this B here depends on the boundary values. It's like which are prescribed. It's like by the problem. Okay, so let me just stop here for a minute. It's like, and then the next thing I'll do is to talk about the actual algorithm to implement this. So I'll stop here for now.